It's time for us to talk about a topic that is really sort of a sore subject for a lot of people, and that's the idea of centripetal versus centrifugal force. Now, we're going to be looking at circular motion here and the idea of fictitious forces, but before we look into centrifugal force, let's consider a situation. Let's say that you were riding in an elevator, but this is no elevator, no ordinary elevator. This is a space elevator, and you're riding in this space elevator, which happens to be powered by rockets, of course, because that's how you do everything in space. And this space elevator that was at rest suddenly starts to accelerate upward with you floating around in the middle. Accelerates upward, and bam, you hit the floor of this space elevator. And what happens after that? Well, you continue to stay on the floor of this space elevator. Now, if you were in this sealed elevator, didn't know you were in space, you knew that you were floating around one moment and suddenly you were at the floor, it'd be completely reasonable to assume, gee, there must have been something pushing me down toward the floor. Maybe there's gravity here. You're going to stay at the floor of the elevator, and you could do something like stand or do jumping jacks or have a cup of coffee, and it would feel just like it would if you had gravity. And if this elevator were accelerating upward at say 9.8 meters per second squared, then it would feel exactly like it would be completely indistinguishable from being on the Earth. You would have that same amount of force that exists between your feet and the floor that you're used to, that same normal force that you feel in your feet, and you wouldn't be able to tell that there was no measurable gravity around you. Now, does that mean that it's correct to say that there's gravity acting on this person downward because they feel this force in their feet? They can stand on the floor without floating around? Well, yes and no. For the person inside the elevator, that's a reasonable explanation, and he could do calculations of his weight or the amount of energy it takes for him to jump up into the higher parts of the elevator, and those calculations would be the same whether there was gravity pulling him to the floor or whether it was the elevator accelerating upward that kept him at the floor. But from the outside, we can see that no, there's no downward force acting on him. It's just that the elevator was accelerating upward and he didn't get out of the way. Well, when we describe that situation using a gravity force pulling him downward, we'd call it a fictitious force. It's a force that explains the situation, but from the right frame of reference, from the right perspective, we can see that there's nothing down below him here to be pulling him downward by this force of gravity, at least not as strongly as he's feeling it. Centrifugal force is a lot like that. Centrifugal force is this perceived force toward the outside of a circle. You feel it when you go around a corner in a car. You get pushed toward the outside of the car, pushed toward one of the doors, and it makes that lean game fun when you're kids and you have the opportunity to squish your little brother or sister against the door, and I can't help it because I was being pushed by this force toward the outside, this centrifugal force. But you weren't. Actually, you were moving in a straight line, and it was the car that was accelerating, and it wasn't accelerating outward from the middle of a circle, it was going inward toward the center of the circle. You just failed to get out of the way of the door of the car. Now, if we have this object that's going around in a circle, and we have no forces acting on this object, then, well, it's going to travel in a straight line instead of a circle. That's Newton's first law. Objects in motion, they continue in motion in a straight line at a constant velocity until they're acted on by some outside force. If there were a force going away from the center of the circle, we had this motion downward, and we have a force outward, we'd see this curving away from the circle. But instead we see this curving toward the center of the circle. The only way to explain that is if we have a force that points inward toward the center of the circle. And that force, since it's in that direction toward the center of the circle, we can identify it as being a force in the centripetal direction. I think people get hung up on this idea of centrifugal force. They think that there's some new force that exists because of this circular motion. Centripetal and centrifugal are just words that express direction, kind of like we've had forces in the x direction and forces in the y direction so far. Now we're going to have forces in the centripetal direction. It turns out that we can figure out how much force is required to make this object go around in a circle, and it has to be an overall force toward the center of the circle. We can figure out how much it takes using an equation, and so the amount of force that it takes to make an object go around in a circle is going to depend on how massive that object is, how fast that object wants to go around in this circle, and the radius of that circle that it's traveling on. And so just like with Newton's second law before, we had net force equals mass times acceleration. Well, here net force is going to be mass times centripetal acceleration. And we've already dealt with an equation for centripetal acceleration. That was, just write that was acceleration in the centripetal direction was v squared over r. So the Newton's second law equation, when we're talking about circular motion, says the net force in the centripetal direction is equal to mass times velocity squared divided by the radius of this circle. Now keep in mind that this term, the net force in the centripetal direction, that can be made up of a number of different forces, some pointing toward the center of the circle, others pointing away from the center of the circle, but none of those forces is going to be the centripetal force or the centrifugal force. Centripetal and centrifugal just tell us direction. We're going to have things like tension and normal force and friction that can be centripetal and centrifugal forces, but again, we're thinking of this as just being the same as force in the x direction or force in the y. We don't have a force called the x force or the y force, and we're not going to have a force called the centripetal force. Now, this relationship is different depending on the situation. Or the relationship holds true, but how we use it differs with the situation. For an object traveling in a horizontal circle, things are pretty consistent. We can have a constant speed going round and around. If we have more of a vertical circle, though, we know that object's going to speed up as it moves down, as it gets lower. So that complicates the issue a little bit. So let's consider a case like that. We're actually not going to look at an object going in a complete circle here, but as long as it's traveling on an arc that could be a part of a circle, we can still use these same relationships. So we'll use the example of a pendulum. This pendulum has a length of 2 meters and has a bob, that's the weight at the very end, it has a bob whose mass is 4 kilograms. We're going to pull it back to an angle of 35 degrees and release it from rest at this position, and it's going to swing down, and at this point, at the very bottom, it's got to have some tension in this string. We want to know how much tension is in that string, and we'll solve this using that net force in the centripetal direction equals mass times centripetal acceleration. So if I looked at this situation in terms of the forces acting on this this bob at this point. So I've got my mass right there. I've got two forces. I have tension going upward and gravity pulling downwards. That'll be a weight force equal to mass times the gravity, the acceleration of gravity there. And we know that overall we have to have a force that points upward toward the center of the circle, toward that point where the bob's attached. Otherwise, this object isn't moving in a circle, it's falling off the string or falling off the anchor point there. So I know here that my net force in the centripetal direction has to be equal to mv squared, and usually we write that as a vt, that's tangential velocity, mvt squared over r. And then I'm going to substitute the forces that act either toward the center or away from the center of the circle. Here I've got tension, which is toward the center of the circle, and then I have weight that's away, so I'm going to make that a negative weight is equal to mvt squared over r. We want to know what the value for the tension is, so that means I need to figure out everything else in this equation. So I need to know the weight. Well, that's easy enough. I can do mass times 9.8 to get that. Need to know the mass. Got that, 4 kilograms. Need to know the radius. Well, that'd just be the length of the string here, 2.0 meters. And I need to know the velocity at this point. That part isn't given to us. So we're going to have to do a little bit more work before we can come back and solve this equation. If we look at this in terms of energy, we can see that in our initial state we've pulled our pendulum back to some height and we've dropped it and let it swing down, and then it gets down to some minimum height here, so it's lost as much gravitational potential energy as it can, and it's picked that up in the kinetic energy, so it's gotten faster and faster as it's fallen. So we need to solve this part as a conservation of energy problem. Total energy initial equals total energy final. And in this case it's going to be gravitational potential energy on the initial side and kinetic energy on the final side. So I can plug in equations for that. It's mass times gravity times height initial is equal to 1/2 times mass times final velocity squared, and you can divide both sides by m and get just gravity times initial height is equal to 1/2 mv squared. Oops, 1/2 just v squared now. And if I isolate v, I get the equation v is equal to the square root of 2g times h naught. So now I can solve for v because I know, well, 2. I know gravity is 9.8 meters per second squared downward, and I know that h naught is, well, I guess I don't know h naught. We're going to have to do a little bit of geometry to figure that out. So I know that h naught is going to be, let's see, the distance from here to here. So how high it was at the starting point compared to the ending point. So I need some way to figure out that distance. Well, I know that this whole distance here is that 2.0 meters. And then this distance I can figure out by treating this thing as a right triangle, where I have an angle of 35 degrees there and a hypotenuse of 2.0 meters there. So in this one, I can solve for that by doing, I'll call this the y, the vertical amount there. So I can find y by doing 2.0 meters times the cosine of 35 degrees. So then y is going to be equal to 1.64 meters. And I know that y plus h naught, since those two make up this entire distance together, that has to equal 2. So that gives me h naught must be 0.36 meters. So come back down here and substitute in that 0.36 meters. So v is equal to the square root of 2 times 9.8 meters per second squared times 0.36 meters. So V is going to be equal to, whoops, that's 0.36. There we go. Square root of 7.06, and that'd be meters squared per second squared. And then I'll square root both sides. And get V is equal to 2.66 meters per second. And now I can come back up here and continue this one. Got tension minus, let's see, the weight would be 4.0 kilograms times 9.8 meters per second squared is equal to 4.0 kilograms times the velocity I just found, 2.66 meters per second. That whole thing gets squared, divided by the radius, which was 2.0 meters. So tension minus, let's see, 4 times 9.8, that'd be 19.6, 39.2 newtons, and I added that to both sides, plus, let's see, 4 times 2.66 squared divided by 2 is equal to 14.2 newtons. And so my tension then would be equal to 53.4 newtons. And something we can see here, since that tension depends on let's see, weight, which doesn't change, and mass, which doesn't change, and radius, which doesn't change, and the velocity, which is the only thing in that changes, we can understand that when velocity is at a maximum, tension will be at a maximum too. And when is velocity at a maximum? Well, it's at a maximum when it has a minimum gravitational potential energy, because all that energy has been changed into kinetic energy. Or in other words, it gets to a maximum at this bottom point right here. So the final state that we've picked out here, that's always going to be the maximum tension point. So sometimes these problems, they won't ask you what's the tension at the bottom of the swing. They might say, what's the maximum tension during this pendulum swing? That's really the same question. They just are asking you to know that tension has to be a maximum when this thing is going at its fastest, which happens at the very bottom of the arc.